Hi everybody, Physics Ninja here. Today what I want to do is I want to apply Gauss's law to an infinite sheet of charge. So we'll start off by just looking at the electric field produced by positively or negatively charged sheets of charge. And then what we're going to do is apply Gauss's law, figure out a Gaussian surface for this sheet of charge and use it to calculate the magnitude of the electric field produced by these sheets of charge. We'll consider one sheet, and then actually we'll also consider how do you apply these results in order to calculate the field between a parallel plate capacitor. So two sheets of charge separated by a certain distance, how would you find the field everywhere in space produced by these charge or by this charge configuration? All right, like with all my videos, if you like it, give it a thumbs up. Consider subscribing to my channel. It's the best way to support what I do. All right, let's get started. All right, we're going to start off by considering a two-dimensional sheet of charge. And that sheet of charge is basically going to be very large, okay? That's why I'm kind of showing those arrows over there. That it basically extends to infinity. Now, in reality, it's not really going to infinity. As long as we're close to this sheet of charge, for example, if I wanted to evaluate the electric field right here at this point P, and as long as that distance z is not too high above it, then even if it was a finite size, then it would look like it's practically infinite. It would behave similar to an infinite sheet. All right, so this is kind of an approximation. Now, there's two things that can happen with this sheet of charge. Number one is it could be positively charged, as in the case here up above, okay, or it could be negatively charged, okay? Now, what we're going to do in this video here is we're going to consider the case where the charge is uniformly spread out on the 2D sheet of charge. So, and what we do in order to define that is we define something called a surface charge density. All right, and the symbol that we use to denote that is typically the letter sigma. Okay, so this denotes the surface charge density. Now, in terms of an equation, what it means is that sigma is defined as the total charge on that sheet of charge divided by the total area. Okay? And we're assuming that this value here is a constant. So if you look, for example, at a small little section over here of this two-dimensional sheet, if I look at it and it has a little bit of charge, well, that's because it has a little bit of area. Okay, and we're assuming that this here is uniform anywhere you would look. All right, and so what we're going to have, for example, for this positively charged sheet, we might have a sigma here, which equals to, for example, +5. And that would have units of coulombs, for example, per meter squared. This would have a charge density or a surface charge density. If it was negatively charged, a different sheet here might have a surface charge density, which might be -3 coulombs per meter squared. All right, it's negative because all of the charges on the sheet are negative values. All right, and it has the right units here. So this would be the sigma for this negatively charged sheet of charge. All right, so now what we want to do in the next case is look at the electric field now produced by one of these cases. Let's start off with the positively charged sheet shown here up above. All right, we first start off with our positively charged two-dimensional sheet, and it has a charge density sigma here, which is the total charge divided by the total area of the sheet. Now, what I'm going to do here is I'm going to slice it, okay? So let me introduce a slice just to make kind of it a little bit easier to see, because working in 3 dimensions can sometimes be a little bit complicated. So if I slice this two-dimensional sheet and I look at it from the side view, it basically looks like this. All right, so let's just first look at this bottom picture of the side view and consider the electric field produced by this. Now, we have to remember that this is considered to be very large, right? So it extends in both directions in this slice view, basically to infinity in both directions. All right, the first question I have is, what is the direction of the electric field produced by all of these positive charge on this 2D sheet? And here I'm just showing you the slice view again. Well, what we're first going to do is consider a point simply just above the sheet right here. And I want to plot the electric field produced by a few charges. Let's consider this guy. Since it's positively charged, it produces an electric field that is vertically upward. All right, and I'm just going to call that vector here E1, all right, because that is charge number 1. Well, let's look at a charge that's a little bit to the side. Let's consider this guy right here. This is charge 2, and it produces a field that goes in this direction, right? It points away from that positive charge. So for this one, this is the direction of the electric field produced by that charge number 2. Now, every time there is a charge that is a distance away from the center one, guess what? There's an equal and opposite charge on the right-hand side. So let's label this one here 3. It's the same distance away from the center one, so it's going to produce an electric field that points radially away from this positive charge. However, it's going to be the same magnitude as E2. This is the field E3. Now notice these two vectors here, E2 and E3, have to have the same length because they're exactly the same distance away from each other. And if you have a large sheet like this, you're always going to run into this situation, right? Whenever there is a charge on this side, there's an equal and opposite charge that's the same distance away on the other side. So your goal at the end would be to add up all of these vectors, right? If I sum up every single vector produced by this, guess what you're going to get at the end of the day? You have to have a vector that points away from the sheet of charge. E total must point away from it. And it doesn't matter where you consider this because it extends in both directions to infinity. So E total everywhere has to point directly outward, perpendicular to the sheet of charge. Now, it doesn't matter also if you consider a point above or a point below. You're going to get the same situation. So your total electric field produced by a two-dimensional charged sheet, guess what, has to point perpendicular. All of the horizontal components are going to cancel out once you add up all of these vectors together. Okay, so that is a very, very important aspect of two-dimensional sheets of charge, okay, that the total electric field points outward if it's positively charged. Okay, now similarly, if the sheet of charge has a negative charge density, then if you use the same arguments, you have to be able to understand that the electric field must point toward it because it's negatively charged, and that's the convention. But again, that the electric field must be perpendicular to the sheet of charge. It cannot have any component that is parallel to the sheet of charge because they're always going to cancel out because this goes very, very big, or we're very close to it. So it appears very, very big. All right, my goal now is to apply Gauss's law, which says that the integral over an enclosed surface of this quantity E dot dA has to be equal to Q enclosed divided by epsilon 0. This is simply a definition. And my sheet of charge here has a charge density sigma. So we first have to consider an enclosed surface. So here's one choice for an enclosed surface. I'm going to consider a small little can. Okay, a small little can looks like this. All right, so how do we simplify Gauss's law? Well, we're going to first start with the left-hand side of Gauss's law, okay? The left-hand side is the hard part, okay, which basically says this. The integral of E dot dA, okay, over this enclosed surface right here. This is a total surface. Now, what I'm going to do with this surface here is, well, we're going to label a few things. So this is going to be the top, okay? I'm going to call this here the bottom. And then here we have the side. And I have to evaluate this integral over this entire surface. Well, guess what? I can rewrite this in terms of 3 different integrals. I have the top of E dot dA. Guess what? Plus, I have to add it to the bottom. The same term, E dot dA. And then I also have to integrate the side, right? E dot dA. Now that dot is a dot product, right? This is a scalar product between 2 vectors. Well, let's go ahead and define all these vectors, right? What is the vector E? Well, we just looked at that a little bit. We definitely know the direction of E, all right? E here has to point away from the sheet of charge, right? This is the direction of the electric field at the top surface. At the bottom surface, guess what? The field must point away from all these positive charges. So this is the direction of the electric field At the bottom surface, guess what? At the side, well, the electric field is still pointing. If you're on this top side, the electric field still points away from the positive charges. It still points like this for on the side surface, everywhere on the side surface, right? Okay, so next vector we have to have is this vector dA. What is this vector dA? Well, it has a magnitude and a direction. The magnitude is simply a little bit of element of area, but the direction is this guy, okay? And what this is a vector, this is normal to the surface that I'm considering. Normal is simply another word that means perpendicular to that surface. Let me go ahead and plot that in orange. So if I look at the top surface, guess what? That little vector n points like this. It's perpendicular to the top surface. If I look at the side, well, the perpendicular direction to the side is this one. That is the vector n. And what's the same over here? That's the vector n. And now at the bottom surface, guess what? There's the vector n. Now we should notice a few things. At the top, look what happens. The vector e and the vector n are what? They are parallel to each other. Likewise, down here at the bottom, they are parallel to each other. The interesting part is right over here on the side surface. Look what happens on the side. The vector e and the vector n are perpendicular to each other. When you have vectors that are perpendicular to each other, their scalar product has to be equal to 0. So for the sides, whenever you have this, E dot dA, again, if you remember the definition of a scalar product, it's the magnitude of one vector, it's the magnitude of the other vector multiplied by cos of the angle between both of those vectors. Since for the sides, guess what we have? We have cos of 90 degrees because they're perpendicular to each other. So this has to be equal to 0. So that is a great simplification for us, that this whole integral on the side equal to 0. And it doesn't matter if you consider like a can like this, or if you consider a cube for your box, okay, for your enclosed surface. It doesn't matter. All the integrals on the side are going to be equal to 0 because the vectors are perpendicular. So we're left with two terms, okay? And what we're going to do is use this definition of scalar product, except now the angle theta at the top and the bottom is 0, and cos of 0 is equal to 1. So this is what the top integral looks like. The top integral now looks like E dot dA, that's over the top, plus the bottom. E dot dA is simply E multiplied by dA because you have cos of 0 that comes in here. So that's it. Now, another very, very important argument we have to make, okay, is that this electric field right here, the one, say, on the top surface, it must be the same as the electric field right here. Now, you have to think about this for a minute. Why is that? Why do these fields have to have the same magnitude? They have to have the same magnitudes because, again, you're considering a sheet that is basically infinite on both sides, right, or very, very far from these points. So every time there's a charge on one side that's producing a field, there's a charge exactly on the opposite side. And it doesn't matter where you consider this point right here, whether it's a little bit to the left or a little bit to the right, it doesn't matter. It's going to produce the same field. That means that this field is constant over this entire area right here. And if it's a constant, it means you can take it out of the area. So you're left with this. So you take the E out of the area, and you're left with simply integrating the area at the top plus a similar term for the bottom surface. Okay, well, what is this term? This means I'm integrating over the total top area. Well, that is going to be equal to what? It's going to be equal to this entire area right here. Okay, whatever area is of that pillbox right there, that is the area that is, when I add them all up, I'm going to get an area A. All right, so this term over here then becomes simply E multiplied by A after you integrate, add up all the little elements of area. The next term here over the bottom is similar, right? If I add up all of the little bits of area right here on this bottom surface, I'm simply going to get the total area of that surface. So at the end of the day, what we have is this left-hand side of Gauss's law, which looked very complicated to begin with, simply boils down to this: 2 times the electric field magnitude at this top surface multiplied by the area of that top surface. All right, that's it. All right, let's go on the next page and look at the other side of Gauss's law. All right, now I want to look at the right-hand side of Gauss's law. The right-hand side looks very, very simple. Simply says it's how much charge is inside this surface divided by this number, this permittivity of free space. Look it up in a book. So in order to find how much charge is enclosed, well, we're going to use the fact that we know that there is a constant charge density. So all we're doing here is we want to know how much charge is here, right? Well, guess what? This little box, remember, had an area equal to A. If it has a charge density sigma, then the charge enclosed is simply the charge density, the charge per surface area that you have here, multiplied by the area. Okay, that is the Q enclosed. And now you can't forget the epsilon 0 right here in the denominator. So now you have to put everything together. The left-hand side must be equal to the right-hand side. So you have 2EA must be equal to the charge density sigma, the same area divided by epsilon 0. Now look what we have. We have the area on both sides. Guess what? You can cancel it out. We can bring this 2 down there in the denominator. And at the end of the day, we get that the magnitude of this electric field right here has to be equal to sigma divided by 2 epsilon 0. Okay? That has to be the magnitude of the electric field produced by a 2D uniformly charged sheet. All right, let's apply this result here to a few simple cases. Here's my first one: find the electric field everywhere if my charge density is 4 nanocoulombs per meter squared. We just used Gauss's law. We found that the magnitude of the field was given by this, sigma divided by 2 epsilon 0. Guess what? This is going to be a constant value, right? And basically tells you the magnitude's the same everywhere you look. Now remember, I'm only showing you a small section, but this is basically a 2-dimensional infinite sheet right here. So we know that the field has to point away from it. So everywhere above, the field must point up like this. At any point below, the field must point down, right? Point away from it. And it doesn't matter how far you are, it's an infinite sheet. And the field is always constant, right? So even if I look down here, the electric field is still the same as it is right here. It doesn't matter, right? Even all the way down here, the electric field still has the same magnitude. Well, now you can substitute the values and find how big is this electric field or this one. They're all the same. The electric field then is simply given by this. So 4 nanocoulombs, it's 4.0 times 10 to the minus 9 to convert it to coulombs, divided by 2 times epsilon 0 is 8.85, multiplied times 10 to the minus 12 if I have that in the right units, in SI units. All right, you substitute the values in there. What you're going to get is an electric field magnitude, which is approximately 226, and that is in newtons per coulomb. That is how big this electric field is above and below this 2D charged plane. All right, pretty straightforward. And again, it doesn't matter how far you are away from this infinite sheet right here. Okay, it is a constant field everywhere. Notice that the direction is different though, right? At the top, it's going up, and at the bottom, it's going down. All right, here's another example now. What if I wanted to find the field everywhere, and my system now is composed of 2 different 2-dimensional charge sheets? We have a top one which has a positive charge of 4 nanocoulombs per meter squared, just like the one I just found. All right, and the bottom one now has a negative charge, surface charge density, but it has the same magnitude, right? So how would you go ahead and find the field everywhere? Well, let's first consider the blue one, okay? The blue one is positively charged. We just found that the electric field produced by this one points away from it, right? We just talked about that one in the first example. Let me go ahead and plot the vectors in the 3 different regions here. Let me go ahead and just extend some of those down here, right? Again, these are still all the electric field produced by the positively charged one. It points away from positively charged objects. I know that the green one, the blue one rather, the magnitude we just calculated was 226 newtons per coulomb. That's how big this field was here, E, the blue one. Now let's go ahead and consider the negative one, okay? We have a negative charged sheet. Guess what? The electric field produced by a negatively charged object must point toward it. And Gauss's law told us that, well, guess what? First of all, the symmetry told us that it would point toward it, right? So you can go ahead and draw all those vectors, right? And they must point toward the negatively charged sheet. Let me go ahead and just plot them in all the different regions. All right. Now, since the magnitude of the charge is the same, right? We know we can calculate the magnitude of this. It's going to be the same thing as what we did for the positive one. All right. Now, if you put, I'm only considering the magnitude here. So if you put a negative value in here, negative value simply means that the field is pointing toward that object. And we know that from the vectors that I drew. But the magnitude is simply going to be 226 newtons per coulomb because the charge density is the same. All right, I have to have the same value. The thing that makes it different is the field points toward it instead of away from it. Now consider the different regions and look what we have here. Okay, look at in region 1. Wherever there's a blue vector, there's a red vector. And look at those vectors. They're always pointing in opposite directions. I have a positive 226 and I have a 226 pointing in the opposite direction. Call that negative if you want. When I add them up, guess what I'm going to get? If I add up the total, it has to be equal to 0 right here. Okay? Because those vectors are equal and opposite. Likewise, anywhere in region 3, right? We have vectors in opposite directions, and those vectors have the same magnitude. They have the same magnitude because the charge density has the same magnitude in both cases. So the total field in region 3 right here must also be equal to 0. Now, look at what happens in region 2, right? In region 2, it's a little bit different. Look what we have. We have two vectors that point in the same direction, right? So if you consider right here, region 2, first of all, the total electric field has to be pointing like this, right? Has to go away from the positive and toward the negative. And what are we going to do? You're basically adding two of those, right? So my total electric field is going to be adding two of, well, the individual one. Look what happens to those twos. This was from an individual plate, and now the two becomes adding two contributions that are the same. So the total electric field then has to be sigma divided by epsilon 0. Okay, that is between the plates. So very, very important. Now, if you calculate the magnitude for this case, well, guess what? You're simply going to get 2 times 226, right? 226 plus 226 should give me 452 newtons per coulomb. Okay, so this field right here has to be 452 newtons per coulomb. Okay, we're using superposition now to add up the fields produced by each individual two-dimensional sheet. All right, hopefully this makes sense to you. All right, so to summarize right here, this is basically the result, right? If you have one charged sheet, if it's positively charged, field points away. If it's negatively charged, it points toward. The magnitude of the electric field is given by this, the charge density sigma divided by 2 epsilon 0. If you stack now, or if you have a capacitor, right, two charged plates separated by a certain distance like this, now they each will produce the field given on the left-hand side. However, when you add them up as vectors, you end up getting twice the field in between the plates, right? There's two things that are producing an electric field. All right, so, and outside, typically the field is very, very small. Okay? All right, that's it for me, folks. Thanks for watching.